Yeah, so the setting of this talk is going to be the Grassmannian. I'm going to start by introducing that. I mean, one of the issues with this being a kind of remote conference is I don't have a very good sense of who the audience is. I mean, I'm a mathematician, so it's going to be a sort of mathematically themed talk, but I'll try and introduce what I'm using, and I'm happy to take questions throughout if there are any. So the setting is going to be the Grassmannian, which is a projective variety whose points parameterize or just are k-dimensional subspaces of an n-dimensional vector space, which I'm just going to take to be Cn. So it's a very classical mathematical object, and it's you'd say very recently in physics in the definition of the amplitude hedron and these scattering amplitude calculations. So it comes with a very useful set of coordinates on it, which are indexed by subsets of the numbers 1 up to n having k elements. So I'm going to use notation a bit and use this binomial coefficient just to mean the set of k element subsets of 1 up to n. And so then, as I say, this object has particular coordinates on it called the Plico coordinates. And I'll call them delta I, and there's one of these for each one of these k element subsets. And just for orientation, I don't really use this, but it's good to know what we're talking about. If I write a k-dimensional subspace of C to the n as the row span of some matrix, so here M is a k by n matrix, then the value of the ith Plico coordinate on this subspace is the determinant of, well, I'll write mi1 up to mik. So what's going on here is that this k, this set I consists of the indices I1 up to ik, and mi is the ith column of M. Yeah, so M is a k by n matrix. I have this list of k numbers, so if I just pick out k of these k columns, I get a square matrix. I can take its determinant. So that's what the value of this function is. Okay, so these are projective coordinates on this variety. They're not independent. There are relations between them, but these are the standard set of generating functions on this space. Okay, so to study this, I'm going to use some objects which are perhaps a bit more familiar to some of you. Diamond models or big graphs or brain tilings, many names for these things. And so the exposition I'm going to be following is a kind of summary of various pieces of work by Postnikov, by Postnikov and Speyer, Miller and Speyer, and almost certainly other people. So I'm going to let D be a consistent diamond model, but where you might be used to thinking about such things on the torus, mine are going to be in the disk. So as a proper board talk, I'd lift one up to reveal something now. Let's just pull it up from further down. So here's an example. So rather than drawing my bipartite graph in the torus, in a closed surface, I draw it in the disk, which is the surface with boundary. And the other little difference I have is that rather than just being an honest bipartite graph with black and white nodes connected by edges, I also have some half edges which just go from a node, hit the boundary of the disk, and then stop. So I'm thinking of these as half edges which only have one node on the end. Right? And there are n of these. N is 7 in my example. Okay, but that's that's roughly what I'm talking about. Consistency, I'll comment a little bit more on later, but you possibly have some intuition for that already. So combinatorially, the interesting thing I can do with D is try and choose a perfect matching of it. So a perfect matching is a set mu of edges and half edges. So I'm allowed to use these funny things at the boundary, which cover each node exactly once. Okay, so let's give an example. So I can choose, say, these proper edges. Now I still have 3 nodes which are uncovered. Let me cover them by their half edges. Right, and now you should see that every node in this graph is incident with exactly one edge which has a purple squiggle on it. Right, so the purple things are my matching mu. Right. And so given such a perfect matching, it comes with a boundary value, or just write boundary of mu. And this is computed in a slightly odd way. So the first thing I do is I look at the half edges in the matching such that their one endpoint is white. And each one of the half edges has a kind of index on it. I've numbered them by one up to n, and I'm going to record those indices, right? And then I do something very similar with the half edges where the one endpoint is black, but now I'm going to record the ones which are not included in the matching. Right. So what I do is a bit different depending on the color. So in this example, so half edge 1 is white and included. So 1 is in the boundary value. Half edge 2 is black and not included, so 2 is in the boundary value. 3 is white, but it's not included, so there's no 3. 4 is black but included in the matching, so there's no 4. The next one is 5, and then 6 and 7 are not included. So in this example, my boundary value is 1, 2, 5. Right? And if you just do a bit of counting, what you'll see is that independent of the matching I actually choose, this boundary value is a k-element subset of 1 up to n, where n is just the number of half edges. So that much is kind of clear. And for k, you have to do a little bit of work, but you can count it. It's the number of white vertices minus the number of black vertices plus the number of half edges whose endpoint is black. Okay, so in this example, it's 3, right? So this will be this k will be constant for all perfect matchings. They all have the same size boundary value. Okay, and now I'm going to count these things, but I'm going to count them by a kind of generating function. So firstly, if mu is a perfect matching, I kind of record it via a monomial mu of y, which is just the product over the edges in the matching of some sort of formal variables, one for each edge. So initially, this is just a very strange way, in some sense, of writing down what the matching actually is. I just multiply together some variables, one for each edge included in the matching. Right? Now I'm going to do a change of variables. So if I look at some edge in my graph, or a half edge, the principle will be the same, but I'll just draw it for a full edge. So this is the edge E. Well, that edge is between 2 faces, which I'll call E plus and E minus, and I can tell which one is plus and which one's minus using the colors of the nodes. So I'll change into some variables called x. So mu of x is then the product, again, over edges in mu of xe plus divided by xe minus. Okay, so now I have one variable for each face. And on the edge, I put the quotient of the two adjacent faces. Right? And then I just substitute those values into my original mu. So that's, okay, it's not clear why I'm doing that, but it's certainly something I'm allowed to do. Right? And so now I have a kind of count. So yeah, do that. So if I write F for the set of faces of the diamond model of D, so these were the components between the edges, the components of the complement, which I used here. What I can do now using this combinatorics is write down a map mu underline, which goes from a torus whose rank is the number of faces, and it goes into this Grassmannian k-dimensional subspaces of 1 up to n. And okay, what does it do? Well, if I apply mu to a point x in this torus, the only way I can describe for you where that is in the Grassmannian is to tell you the lookup coordinates. Maybe let me write this on the line below. And so if I evaluate the ith lookup coordinate on mu of x, then what I get is the sum over matchings whose boundary value is I, is this index mu of x. Right? So mu of x is if x is a point in this torus, then mu of x is a complex number. I just add them up over the matchings with a fixed boundary value. This guy is called the dimer partition function. Okay. So it's a non-trivial fact that this map actually does take values in this Grassmannian. Right? I said the lookup coordinates are not algebraically independent things. They satisfy certain relations. And so you have to prove that these quantities satisfy those relations. Right? That's something that people have done. But in any case, I get a map. Sorry, yes?
I is an integer number, or is it a collection of numbers?
I is a k element subset of 1 up to n, so it's k numbers. Yeah. Okay, so I get a map from a torus with rank equal to the number of faces into the Grassmannian. Okay, so that's one piece of combinatorics. Let me tell you another. So I can also label the faces of my diamond model by k subsets. Now, to do that, I need to tell you about strands or zigzag paths. So again, I think this will be familiar to some of you. So I draw strands on my diamond model according to the following rules. So I walk along the edges. When I come to a white vertex, I turn left as far as I can. When I come to a black node, I turn right as far as I can. So sorry, if I just scroll down a minute. Again, I prepared one earlier. So this is what happens if I do this in my example. And now is the right time to comment on. So consistency for me as a combinatorial condition, it's rules on the crossings of these strands. So I won't give details here, but this is how consistency is defined. These strands should cross in particular ways. Okay, but then if I choose some face of my diamond model, I can write down a label IF by recording the indices I such that, and again, I'll just draw a little schematic. So if I look at the disk, I find I, which is supposed to be a number from 1 up to n, somewhere on the boundary next to a half edge. Some strand will start there and go through the disk until it ends. And I'm going to record the indices I, which have my chosen face F on their left, on the left of this strand. Okay, so let's do that. So the strand starting at 1 has these two faces in the boundary on the left. The strand 2 has rather a lot on its left. So it has this one, and this one, and 2 in the middle. The boundary in the interior will play slightly different roles. I'm going to use these 2 colors just to make it clear what we're looking at. 3 shows up here, here, and here, for example, and so you can continue in this way. Let me just give the answer now. You get the following labels on the faces. List that one out. 147, 247, 245, 457. Okay, so you can check that hopefully I did that correctly. And so the magic is that every one of these labels has exactly k elements in, so the same k that's been appearing throughout. Okay, so the fact that they all have the same size is not so hard. The fact that this number is k, like the same k as before, is a bit more subtle. Okay. Again, doing this operation allows me to write down a second function. Now, starting in the Grassmannian and mapping to a torus, again with rank equal to the number of faces. And now the recipe is much simpler. I just take a point in this Grassmannian, which is some subspace, and I look at its value under the Plucker coordinates, whose index sets are the labels appearing on the faces in the dimer. And I just write that list of values down. Okay. Well, I suppose, yeah, strictly speaking, this is sort of birational, because there could be some points at which some of these functions are 0, so I don't land in the torus. But at least on some open set in the Grassmannian, this is a well-defined map. Okay, very good. So the question that mathematicians ask then is, well, I have this map kind of from a torus to the Grassmannian, was given by this dimer partition function. I have this map C out, but I'm just going to write a solid arrow now, even though it's not. I mean, I claim that C is well defined, at least on the image of mu, so I'm not going to fuss about this anymore. And the question is this map an isomorphism, i.e., so after some change of coordinates, are these local coordinates given by the phase labels just reading off for me where the dimer partition function landed? And the answer is, in fact, no. But this is Muller and Speyer's contribution to the story. There's an additional map called the twist, which goes from the image of mu just back into the Grassmannian, such that if I map from my first torus into the Grassmannian by applying the dimer partition function and then twisting, then when I map out again by this map C, I do get an isomorphism. Okay, so this generalizes some earlier work by Marsh and Scott and by Bernstein, Fehm, and Zelevinsky for particular dimer models who constructed similar twist maps. This one works in general. I'm being a bit circumspect about what the image of mu actually is. It can be some quite high codimension subvariety of the Grassmannian, depending on my dimer model. It actually lands in some positoid variety, if you know what a positoid variety is. I'm not going to dwell on this. So yeah, so it has vertices and it has arrows like an ordinary quiver, and it also has faces, Q2, and effectively all the data of a face is a boundary, which should be an oriented cycle. In the ordinary part of the quiver. And I mean sort of up to cyclic equivalence. So shouldn't dwell too much on this. What I mean is I don't mind where I think this oriented cycle starts and ends. So I'm kind of ambivalent about, I mean, formally an oriented cycle in a quiver has a start point and an end point, which are the same. And by up to cyclic equivalence, I mean, I'm kind of happy to move the start and end point to anywhere on the cycle when I don't think anything changed. Okay, let me show you some examples. I think that's the last time I'll have to pull up something from off the bottom of the screen. So maybe I start on the right. If I have my diamond model, I can draw a quiver in it by the usual construction, which we already saw. The same, nothing changes because I'm on the boundary. It's just that some of the arrows are kind of special because they're boundary arrows, but that only means I'm going to use them differently. They're still quiver arrows. Okay, but because this quiver is drawn in a topological surface, it comes with a natural notion of faces, which are just the complements of the quiver in the disk. And you see that each one of those faces has an oriented cycle as a boundary. So those are what the faces come from, and they correspond combinatorially to the nodes or vertices of the bipartite graph B. Okay, so the diamond model gives you a very natural example of a quiver with faces. Here's another one which is more ad hoc and combinatorial. I just put n vertices, again n is 7 again, in a circle. I connect adjacent vertices by 2 arrows of x, which is clockwise, and y, which is anti-clockwise, and each little 2 cycle xy will be the boundary of a face. Okay. So this we'll call the circle quiver Cn. It just depends on this parameter n. Okay. Okay, so now this setup will help us categorify all the combinatorics that came before, starting with perfect matchings. So if I have a quiver with faces, a perfect matching of it, of Q, is now a subset of the arrows such that every face has exactly one matched arrow in its boundary. Okay, so let me make a copy of this. So if we draw, well, this will get a bit messy, but then I'll tidy it up. So if I draw again the perfect matching example we had earlier, that's this guy. You'll see that picks out for me a set of arrows in the quiver because the set of arrows in the quiver is just the same as the set of arrows in the graph. Okay, and if you stare at this, maybe not fantastically easy to see the way it's drawn, but if you stare at this, you'll see that every face has exactly one of these arrows in its boundary because every node in the dimer has one matched arrow, matched edge adjacent to it. And so the upshot is that a perfect matching of QD, of this dimer quiver with faces, is exactly the same information as a perfect matching of D. Right? So sort of is a clue that we're doing the right thing. And so given such a perfect matching, I can define a representation, B mu, so a representation of Q, by, well, to tell you a representation, I need to say a vector space at each vertex. The vector space is actually always going to be the same. It's going to be Z, which is my shorthand for the power series ring in one variable. So at every vertex in the quiver, I put a copy of this infinite dimensional vector space. This is going to be infinite dimensional representation. And on every arrow, I need to tell you a map. And the map will be multiplication by T for the arrows which are included in the matching and the identity for the other arrows. Right? This will refer to as a perfect matching module. I mean, module and representation effectively mean the same thing. We prefer module. Okay, so now let me sort of sketch this. Put the t's on the arrows which are matched, right? And now let me clear up this picture a little bit. If I remove the actual dimer, just leave the quiver. Now it should be a little bit easier to see that the boundary of every face has exactly one arrow with a T written on it. Okay, so this is sort of what the matching module looks like. Okay, and then so far I've just been working with representations of quivers. I don't have anything. Yeah, I'm just working with representations of quivers. Now I want to introduce some algebras, so I want to put relations on these quivers, and I get some very natural choices. So if I'm working with the dimer quiver, then any one of these perfect matching modules is actually a module over, I mean, it satisfies certain relations automatically. So it's a module for the quotient of the path algebra by relations which say certain paths are equal. So I'm writing this out in notation, which I'll now explain. So what this notation means is that A is an internal arrow, one of the ones I've been drawing in green. And because it's internal, it's contained in two faces, one around a black vertex, and I'll call PA black the path completing A to the boundary of a face around a black vertex, and PA white will be the other one completing A to a face around a white vertex. Okay, maybe I should have kept the nodes here. Maybe help a little bit. Put them back in. Right, so you see that every arrow is contained in one black face and one white face, and so there are two paths completing it. Right, and so you can check that if I write down a perfect matching module, well, then either this arrow A is acting as multiplication by T, in which case both of these two paths are acting as multiplication by 1, which is the same, or A is not T, in which case there's exactly one T somewhere on here, and exactly one T somewhere on here. So again, the two paths are acting in the same way. So these relations hold for all of my perfect matching modules. Okay, so for some slightly technical reasons, I should write this. I should complete. So this is taking the complete path algebra and closing the ideal. This is just to be honest, and I wouldn't really worry about it. Okay, so that's my first algebra. The second thing I'm going to do is use the boundary. So because A comes from a quiver with relations, it has idempotent elements, one for each vertex of the quiver. Right? And I'm going to just add up the ones for the vertices which are on the boundary that I drew in blue, call that E, and then B will be the algebra EAE. Okay, so what's happening here is that while A is spanned by all the paths in this quiver, I mean, modulo some relations, but it's spanned by those paths. B is the subalgebra spanned by paths which start and end on the boundary. Okay, so that's my second algebra. I need one more. So first, a construction by Jensen, King, and Su says that if I take some subset I of 1 up to n, I get a perfect matching mu I of this circle quiver, the other example. And what mu I is it's the set of the arrows xi for I not in the matching together with the arrows yi for I in the subset, not the matching, I should say. Okay, so in any case, let me scroll up a bit, so you lose the definition, unfortunately. So all I'm saying is that if I choose a subset of 1 up to n, I mean, effectively I'm choosing a subset of these n faces. Then to get a perfect matching of this quiver, I have to tell you for each face, I have to tell you either x or y. And this is a rule for doing that based on some subset I. So if you check for each index, I've chosen either xi if I was not in I, or yi if I is in I. So I've chosen one of X or Y in each one of these two cycles. So that's a perfect matching. And the observation here is that for the circle quiver, any one of the corresponding matching modules, so I'll just write VI instead of V mu I, in the case that I has size K, this is a module, again, for some quotient algebra, which I'll call C. It's the path algebra of this quiver, modulo relations, well, xy equals yx, because both of them are t, always, they're the boundary of a face. And the more subtle thing to see, that you can check, is that when the subset has size k, doing ky, so taking k steps in the anti-clockwise direction, is the same as doing n minus k steps in the clockwise direction, n minus k x's. So it's not completely obvious, but it's true. Okay, again, just for technical reasons, I have to complete and close. Okay. So this is the most heavily algebraic part of the talk, but I'll try and bring it back down to earth in a moment. So these three algebras I've introduced turn out to be free and finitely generated algebras over Z over this power series ring. So this is by the three of us for A and B, and it's by Jensen, Kim, and Sue for C. And for any one of these algebras, I get a category of Cohen-Macaulay modules, which are those modules where if I just look at their structure over this power series ring Z, I get a free and finitely generated module. So the crucial thing about this category really is that all of the perfect matching modules I defined live in here. Okay, maybe for some orientation, if the if A was the Dimer algebra from a Dimer model on the torus instead of on the disk, then the derived category of this would be the sort of 3CY category equivalent to some category of coherent sheets under resolution. So this shouldn't be completely alien to things you've seen. But I have a bunch of different situations appearing now because I have the surface with boundary. Okay, so these various categories are related by functors, and the fact that B was defined to be EAE means that I get a restriction functor, which I'll also call E, from A modules to B modules. So that much is effectively canonical. I mean, if you like, I take a representation of A, which is some representation of this Dimer quiver, and I just forget about all the information on the interior and just think about the information on the boundary. A proposition by the three of us is that B and C are also related by an algebra map, which doesn't actually have to have a name. Oops. Algebra map from C to B. So this gives us another restriction functor, which I will call rho, from Cohen-Macaulay C modules to Cohen-Macaulay B modules to Cohen-Macaulay C modules. This functor is actually fully faithful. Okay, so what I'm saying is that the Cohen-Macaulay B modules are effectively a subcategory of the Cohen-Macaulay C module. Okay, so now in the last 5 minutes, I should try and make it clear why I'm doing any of this, so what this has to do with where we started. So the first observation is supposed to explain this slightly peculiar definition of the boundary value of a matching. So the observation is that if I start with a perfect matching of, well, D, but that's the same as a perfect matching of the Dimer quiver, then I can look at its associated perfect matching module. I can first restrict that, this is an A module, I can first restrict it to a B module by E, and then I can restrict it to a C module via rho. And the claim is that the C module it will be is exactly the perfect matching module for Cn given by its boundary value. So this process of passing from a matching to its boundary value is a shadow of the representation theoretic operation of doing these two restriction maps. Okay, so that's a sort of quick observation. This also lets us explain the face label construction, and that takes a lot more work. So every face of my dimer, which is the same thing as the vertex of the quiver, I get a canonical representation of A, which is the projective at that vertex, PF. And the theorem is if I take that PF, that module PF, and I apply the same operation, I first restrict it to B via E, and then I restrict it to C via rho, then the representation of Cn I get is the perfect matching module indexed by the face label associated by this combinatorial rule. So again, this kind of strange, rather ad hoc looking combinatorial rule has an algebraic interpretation as computing something about the projective module, the projective A module of that vertex of the quiver. Okay. And so finally, this twist map, which is the most mysterious thing of all, maybe. I didn't even give you a formula for it because that would have taken a long time and been confusing, but I just told you a key property. So now, I mean, 2 minutes, I'll be a bit vague, but one reason for being interested in this category of Cohen-Macaulay B modules, so B was the algebra in the middle, the boundary algebra of the dimer quiver, is that it has a function called CC for cluster character, taking objects of it to rational functions on the Grassmannian. Right, so I'm just completely black boxing this. I'd say I'm not going to define this function, but one property it has is it takes these restricted projectives, which I was just talking about, are sent to the Plucker coordinates with the corresponding face label. Okay. The fact that this function exists and sort of has sensible properties depends on a lot of the theory, which I'm not going to say because I don't have time. But let me tell you one more thing about it, which is supposed to explain the twist. So if I take V to be some object in this category of Cohen-Macaulay B modules, and I choose it so that if I restrict via rho to C modules, I get one of these perfect matching guys, VIs. So that's for some subset of K element subset of 1 up to n. So the restricted projectives are examples of these I could use, but there are more. Then the claim is if I look at the twist map and I take its ith Plucker coordinate, okay, that's some function on the Grassmannian, say twist and then take the ith coordinate. What that will be is the quotient of the images of two objects in CMB under this map CC. So what I do is I'll have to write it one way and then explain it the other way. So let's write it. So maybe if you're not a representation theorist, this isn't so meaningful, but I promise it's a standard construction in representation theory. I take an object in V in CMB, it's a B module. I take a projective cover, which I'm just going to call PV, and I take the kernel. And that's called omega V, and this operation is called taking syzygies. So omega is a functor on the appropriate category. And the claim is that the ith coordinate of the twist, where I is this I, is computed by taking the cluster character of this syzygy and dividing by the cluster character of the projective. So the slogan that we want to sum up with is twist is categorified by, or is given by this functor omega, which, as I say, is called the syzygy. Okay, so if the first statement, the first sort of question were true, at the beginning I asked whether taking the diamond partition function, following it by this cluster map C was an isomorphism. That would be saying something like this composition should just be the cluster character of V itself, right? But it's not. And the correction is you first have to apply this syzygy functor, okay, and then there's some normalization. And then they line up. So it's the syzygy that is categorifying the twist. Okay, sorry, I'm 2 minutes over, so I'll stop now.
Thank you very much for the very interesting talk, Mark. Are there any questions in the audience?